Welcome back to the Deep Dive. Today we're going on a pretty wild theoretical journey. We're going to explore gravity in a simplified universe.
That's right. Not our usual three spatial dimensions plus time. We're dropping one.
Exactly. We're heading into what physicists call 2+1 gravity, or maybe more evocatively, Flatland.
And it's a fantastic way to really get at the heart of general relativity. We've got this technical presentation as our source material, and it lays out a kind of a fork in the road.
A fork in the road that determines the entire nature of this universe. It's all about Einstein's equations and how one single mathematical choice can lead to two completely different kinds of gravity.
It's a tale of two geometries. So, to kick things off, we have to start with the foundation.
Einstein's field equations.
Right. And you don't need to, memorize the Greek letters, but the concept is what's key. It's this beautiful equation that says the curvature of spacetime on one side is directly connected to the matter and energy on the other.
Okay, but in our normal universe, that beautiful equation is actually, 10 incredibly complex interconnected problems.
Oh, it's a total beast, a set of coupled nonlinear partial differential equations. It's a nightmare.
It is.
But here's where it gets really interesting. When we drop a dimension, when we go to 2+1, a radical simplification happens.
And what's that?
In a vacuum, completely empty space-time in 2+1 dimensions is always locally flat.
Wait, hold on. That's a huge deal. If it's locally flat, what does that even mean for gravity? If I have two planets just sitting in the flatland vacuum, they don't attract each other.
They do not. In our universe, you have tidal forces. A massive object warps space-time, and that curvature stretches out and pulls on other things from a distance.
Right.
In this flatland vacuum, there's just nothing. The mathematical reason is that the Riemann curvature tensor, the thing that describes tidal forces, just vanishes. It goes to zero.
So gravity only exists exactly where the matter is. It's not a gentle slope in the fabric of space-time. It's more like a puncture.
That's a great way to put it. The influence doesn't radiate out. Gravity is the matter, in a sense. No matter, no curvature, period.
Okay, that immediately leads to the big question then. How do you describe the space-time right around a single massive object? This has to be the fork in the road you mentioned.
This is it. This is the crossroads of geometry. So we try to write down a general description of the space-time around a mass, what we call a line element. And it turns out you need two separate independent functions to describe it. One for time, let's call it A, and one for radial distance, call it B.
Two functions. Why is that a problem?
It's a problem because it's under-constrained. We have more variables than we have equations. There's no single unique solution.
So you're stuck.
Unless you make a choice. You have to impose a condition, an extra piece of information to tie those two functions together. And the choice you make defines the universe you get.
Okay, let's go down path one. What's the first choice we can make?
Path one imposes something called the conformally flat metric. It's a bit of a mouthful, but the idea is simple. We basically force the curved spacetime to be proportional to a flat spacetime. We're saying, let's make this as flat-like as possible.
You're simplifying it, constraining it to behave, in a more straightforward way.
Exactly. And when you plug that constraint into the field equations, you get a solution. Plugging it into the field equations still gives you a pretty tricky differential equation. The math gets a bit messy, involves things like natural logarithms.
We don't need to get bogged down in the nitty-gritty of the formula, but what's the outcome? What does this universe actually look like?
It creates a universe with a singularity at the center, where the mass is. And interestingly, it behaves a lot like good old Newtonian gravity. Particles can have nice, stable, circular orbits.
Does it have an event horizon? Is it a black hole?
And that's the critical part. No, there's absolutely no event horizon.
So it's a super dense point with intense gravity, but it's not a one-way trip. A beam of light could, in theory, escape from anywhere.
Precisely. It's a deep gravitational well, but it's not a prison. That's the universe you get from the keep it simple choice.
A Newtonian-like universe. Okay, so what happens if we go back to that crossroads and take path two?
Path two. This is the more, let's say, elegant choice, the one that leads to something much more exotic.
A black hole.
A black hole. They set B of R to be the inverse of A of R, so B equals 1 over A. And the choice is beautiful. Instead of forcing proportionality to a flat metric, we enforce a kind of symmetry. We just say that function B, the radial one, has to be the exact inverse of function A, the time one. The differential equation that comes out is much cleaner, much simpler to solve.
And the solution?
The solution for A is just profoundly simple. The solution gives us the 2 plus 1 version of the famous Schwarzschild metric, the equation that describes a black hole. We just have to set the constants based on a single property of the mass, a scalar we can call beta.
And that is what makes this a true black hole, unlike the thing from path 1.
Yes. The key difference, the thing that changes everything, is the event horizon. Because we forced that inverse relationship between time and space, the math creates a boundary, a specific radius where the time component of the equation goes to 0 and the space component glows up to infinity.
The point of no return.
That's it.
Yeah.
And it happens at a very specific radius, r equals 2 beta.
Yeah.
Inside that boundary, all paths lead to the singularity. Escape is impossible.
Wow. So the entire existence of black holes in this universe just comes down to that initial, almost aesthetic choice, proportionality versus symmetry.
It's stunning, isn't it? And once you've made that choice, once you're on path 2, the physics of that black hole world is set in stone. We can actually analyze how things move in it.
Okay, let's do that. So we're in the black hole universe.
Yeah.
How do we figure out the path a particle takes?
We use the geodesic equation. It's basically the path of least resistance through this curved spacetime. And from that, we can pull out a kind of energy equation for any moving object.
And this is where that term epsilon comes in from the source material.
Exactly. Epsilon just tells us what kind of particle we're looking at. If epsilon is 1, it's a massive particle, like a planet or a spaceship. It moves slower than light.
Okay.
If epsilon is 0, it's a light ray, a photon. And epsilon equals -1 is space-like, which is the path you'd be on inside the event horizon.
And like in any good physics problem, some things must be conserved, right?
Of course. In this system, both energy and angular momentum are conserved. A particle keeps the same amount as it orbits.
And if you combine those conserved quantities with the energy equation,
You get a very powerful tool called the effective potential. It's basically a graph that shows you the energy landscape around the black hole. The peaks and valleys on that graph tell you exactly where orbits are stable, where they're unstable, and where they're just impossible. The best way to visualize it is like a big roller coaster track. Your particle's energy, E, is its height. If you're high enough to get over the hill, you escape. If you're stuck in a valley, you're in an orbit.
let's start with the fastest thing there is, a photon. Epsilon equals 0. What's its fate near this black hole?
For a photon, the effective potential is surprisingly simple. And when you solve for the critical points, you find there's an unstable circular orbit at a very specific spot,
Where?
at r equals 3 beta.
3 beta. So wait, the event horizon, the point of no return, is at 2 beta. This
Yeah.
is 50% farther out.
It is. This is called the photon sphere. Imagine a photon orbiting perfectly at 3 beta. If it gets nudged outwards just a tiny bit, it escapes to infinity.
And if it gets nudged inward,
It spirals down, crosses the 2 beta event horizon, and is lost forever. That 3 beta line is the last possible place for light to orbit, even unstably.
so there are distinct boundaries. 2 beta is the nothing escapes line, and 3 beta is the last chance for light line. What about for us? For massive things, the time-like case, epsilon equals 1.
For massive particles, you run the math for the effective potential again, and you find another critical radius,
Which is?
the innermost stable circular orbit, or ISCO, and it's located at r equals 6 beta.
The 6 beta. So that's twice as far out as the photon sphere and 3 times the radius of the event horizon itself.
What it means is, if you have a planet or a spaceship in an orbit at 6 beta or farther out, it can stay there forever. It's stable.
But if it dips inside that line, even to 5.9 beta,
It's doomed. There are no more stable circular orbits inside 6 beta. The particle will inevitably spiral all the way down, past the photon sphere, past the event horizon, and into the singularity.
that's incredible.
Now for the last, and maybe the most mind-bending fate, the space-like case. Epsilon is -1. Now, the sources say finding a simple solution here is tough, it gets into complex numbers, but the physics is what's essential.
Right. And physically, epsilon equals -1 represents a path that is inside the event horizon, where r is less than 2 beta.
And our one unbreakable rule is that nothing can go faster than the speed of light, not even inside a black hole.
So something else has to give.
Something has to give, and what happens is that the geometry just warps so profoundly that the radial coordinate and the time coordinate essentially swap roles. The geometry itself, space has to stretch or expand incredibly rapidly to make sure that even though your path is space-like, your local speed never breaks the light barrier.
That's a powerful way to think about it. It's like you're on a cosmic river flowing at the speed of light towards the center. You can paddle left or right, but you're still getting carried downstream.
You are swept up. Time itself is pushing you inward. Inside the horizon, moving towards the singularity becomes as unavoidable as moving forward in time is for us out here.
That's a fantastic visualization. The fate of everything in the universe isn't decided by one line, but by this series of nested, mathematically perfect thresholds.
And it all stems directly from that one choice we made for Path 2. We started with this problem we couldn't solve, this under-constrained system.
Right.
Path 1, the conformally flat choice, gave us a universe that felt Newtonian, no event horizon.
But Path 2, by enforcing that elegant inverse symmetry between time and space,
led directly to this incredibly rich structure, a true black hole with a point of no return at 2 beta.
and it reveals how the geometry of spacetime isn't just one thing, it's this complex landscape with different rules for different things. The event horizon at 2 beta, the photon sphere at 3 beta, the stability limit for matter at 6 beta. This whole deep dive has really been a masterclass in the power of geometry. I mean, 2 simple choices at the very beginning. Conformally flat versus inverse metric, and you get 2 completely different universes.
And the black hole that comes out is governed entirely by those conserved quantities, E and L.
It's incredible.
And what's just mind-bending is that all of this complex behavior, the entire fate of any particle or light ray, is all dictated by these thresholds that are just simple multiples of one single number, beta, which is basically just the mass.
So that leaves you with a pretty profound thought to chew on. If these simple symmetry choices can dictate the entire fundamental nature of gravity and black holes in a simplified 2+1 universe, what undiscovered symmetries might be quietly constraining the structure of our own much more complex 3+1 universe? Maybe the reality we experience is just the result of one perfect, elegant choice made at the very beginning of time.
That is an excellent way to put it.
That's it for this deep dive. We'll see you next time.